Okay, so last installment. I only have 80 slides left now for this last hour that we have to get through. Okay, so now that we talked about the diffusional growth, right, of droplets due to certain vapors, it could be water vapor, it could be other chemicals like sulfuric acid or organic gases, I'm going to tell you most models actually don't do it like this, okay? Some models do, but for another really popular approach, and that has to do with the computational cost, is to short circuit that kinetic, really resolving the kinetics of the growth process, and rather do what's here on the right-hand side, treating everything as being in equilibrium, right? And yeah, so for the next portion, I want to talk about this a little bit, what that means and what goes into that, just so you know how it's done in the various models. And so the left-hand side is basically what we talked about. I don't think I showed you our governing equation anymore, but what we set up with our condensation equation is basically covering this term, right? That underneath the coagulation term was the condensation term. So we've done this now. So it changes the particle composition, the particle size, and you're calculating these mass fluxes. You have to take care of potentially a Kelvin effect and so on, and you're integrating this over time, right? So that's pretty straightforward. But what is actually done in many of our atmospheric chemistry, especially like the 3D, sort of like chemical transport models and global models, is treating this system of aerosol and gas as an equilibrium system. And it actually, there are, you know, for the time scales that we are considering, it works, it can work quite well, but there's also the danger that actually things are not in equilibrium, right? And especially depending on which size of particles you look at, the equilibrium assumption may be violated. And so, but nevertheless, that's one of the important assumptions. We don't actually track the time evolution. We just go from endpoint to endpoint, assuming equilibrium is reached instantaneously. And so this may or may not be violated. Okay, and so what are we then looking at? So our system pretty much may look like this. So we have our gases, right, that are relevant. And so our sulfuric acid that you know, we've heard about, is something that really likes to go into the aerosol phase very easily. There's nitric acid, there's HCl, there's ammonia, there are different organics. That looks very innocent, just one little oval for organics, but there's a myriad of species, right? And they can be different, they have different vapor pressures, but they're all lumped together here. And then we have our aerosol, which may be aqueous, it may not be. And then we have this partitioning, right? And then we have the water, the liquid water, and our ions. And then we also might have solids, right? Not everything may be dissolved depending on how much water we have. And of course, the black carbon doesn't dissolve, and there's other, like dusts, for example, also doesn't dissolve. So there might be a solid portion here as well, and then the aqueous phase. Yeah, so that's pretty much our task. And we probably won't talk much about the organics because we're running out of time. I can see this already. But that's a really big topic in atmospheric chemistry, in aerosol chemistry. Lots of people trying to figure out how these organics are partitioning, what's in them. And so maybe we will get to touch on it a little bit at the end. But let's first focus on the inorganic species. So what's the relevant family of species here? So that's them. We already had them on the previous chart. So where are they coming from? Any ideas where ammonia is coming from, for example?
Decay of horn and so forth.
Yeah, so ammonia is also a fertilizer, right? It's used in agriculture, and cows are producing it, like livestock. Exactly. So and importantly, it's directly emitted, right? For our agriculture. Then sulfuric acid, we already talked about a lot. It's formed, right, and the precursor is SO2. Which may be a result of combustion. There's also another route how you can get SO2, which I don't know you know about, from the ocean, actually. So the oceans are emitting something that's called DMS, dimethyl sulfide. And that DMS can react and form SO2, right? So the sulfur cycle has different components, and one of them actually involves the ocean. Nitric acid, to form that, we need NOx, NO2, and the hydroxyl radical. Now, where does NO2 come from? Again, combustion. It could also be lightning, right? So lightning is a natural source of NO2, and it also comes from soils. Soils emit NO. And yeah. So water vapor we already mentioned. Okay, so that's all going on, and so you see that in itself, trying to figure out these precursor gases and how they are, where they are produced, to what extent they are produced, it's a whole thing in itself, right? So there is a portion of our models, the gas phase chemical mechanism, that tries to do just that. Okay, so I already said this. For the nitric acid, there's actually the one I mentioned, so the OH radical. That's a very important one in atmospheric chemistry. That needs sunlight to be produced, right? So the nitric acid production through this route is a daytime thing. During the nighttime, there is another interesting reaction that can happen that involves the molecule called N2O5. And so that reacts on aerosol surfaces or inside the aerosol and also produces HNO3. So yeah, and that would be an example for a heterogeneous reaction, right? Because it involves an aerosol surface. Okay. Now, at the bottom of this equilibrium considerations is chemical potentials, right? So why do certain things partition into the aerosol phase and not stay in the gas phase? So you have to set up your chemical potentials, and it's all about minimizing the Gibbs free energy, right? So if you are asked, why does something go into the aerosol phase? Well, because the Gibbs free energy is going to be minimized by that new state, and that's why it happens. And so just as a little recap, this is how we calculate these. And let's not worry this example. Let's just show you a few more things here. So here is basically an example of what this might look like, right? For a system that consists of sulfuric acid, ammonia, and water. And the task basically is to figure out, if I give the system these ingredients and I start with a certain temperature and relative humidity, which is supplied by the environment, what happens? right? So how much stays in the aerosol phase, how much stays in the gas phase, what is the equilibrium? And underlying these calculations are the chemical potentials, right? So that's for our thermodynamic equilibrium. Yeah, and so in our community, there are different code bases that are, for the most part, I think maybe all of them are openly available, like open source. Don't quote me on all of these now. We would have to check. But they are used by many people, right? So these thermodynamic codes, there is certain, like a handful, a little bit more than a handful that many people use, and they have their different strengths and weaknesses and assumptions and look at different more or less comprehensive systems, right? So this is just like a three-component system. Of course, in the real atmosphere, we not only have H2SO4, NH3, and water, there are a few other ones that we want to consider. And some of them, most of them have actually many more, but that's how it works. And so some of these go back to the late 1990s, early 2000s, right? And some of them are more or less sophisticated. But what these two figures basically tell us now is I'm starting with a certain amount of sulfuric acid, and then on the x-axis is my ammonia, right? On the x-axis is my ammonia that I'm throwing in. So these, you can imagine, these figures are produced by doing multiple simulations, right? You start out with these ingredients, like H2SO4, and a certain relative humidity, which determines how much water vapor there is. And then you are varying your ammonia, and each point is basically one of these equilibrium calculations. Okay, and I think the thing I want to highlight is just by changing the meteorological conditions, right, relative humidity, from not very high to a little bit higher, you get very different results. So you have the same sort of like mixture of chemicals, right? So on the top, you have the total mass, and then it's split up in the different components that can form, right, in your aerosol. And it doesn't show, here's the total ammonia. Total ammonia is the sum of ammonia in the gas phase and ammonium in the aerosol phase, right? And the other thing that happens is, look at this, like the little annotations. S means solid. So solid, solid. This one is solid. And when you have the ions, it means it's deliquesced, right, with water. So let's pick one case right here. This one, the drier one. So we start out, if ammonia is very low, very low, maybe 0, we have H2SO4, and everything is in H2SO4. Like the 10 microgram that I started with, it's all H2SO4, like sulfuric acid. And sulfuric acid is very, very, very hygroscopic. Even though the relative humidity is low, it grabs some water, right? So that's this point. And we have nothing else. And so the total mass is just H2SO4 and water. And I add this up, and I get this point right there, up there. Now, as you are adding ammonia to the system, H2SO4 goes down, and then water also goes down because we are losing H2SO4, and other things form, right? So this is ammonium bisulfate that forms, and eventually we get ammonium sulfate once we add enough ammonia right here. And after a certain point, actually this point right here, after we lose the sulfuric acid, the water is gone. And so now we are looking at dry aerosol, right, on the right-hand side here. So no water anymore, and the different forms of ammonium sulfate right here, and it's all solid. So relative humidity of 30%. Compare this to 70%. Now we can hang on to the water for much longer, right? So we are adding ammonia again, and calculating our equilibrium at each of these points. We are also losing sulfuric acid, but we are forming these, now we have more available water. We are forming the bisulfate ion right here. Eventually, once we add very much ammonia right here, and we have everything in ammonium sulfate right there, no water anymore, right? So the particle becomes dry, so it can't accommodate any water anymore. So same sort of like amount of chemicals in our system, different relative humidity, big difference to what's happening in the aerosol phase. Okay, so this taking up water or not taking up water is actually, it's a process called deliquescence. And efflorescence is the opposite. And that's a very interesting thing that happens for our aerosols. So now we're talking non-cloud, right? So subsaturated. Increasing the relative humidity from 0 to high values. And on the y-axis, we see it's a ratio of the actual diameter, including the water, divided by the dry diameter. Did you have a question? Okay. And so let's look at the solid line here first, ammonium sulfate. So you need 2 parts of ammonium, 1 part of sulfate forming ammonium sulfate. So what happens for ammonium sulfate particles as we increase the relative humidity from very low to higher, nothing happens, right? So the ratio of diameter, wet diameter to dry diameter, so let's write this down. This is wet diameter to dry diameter. So that ratio stays 1, meaning no water gets taken up until magically it hits the point of around 80% relative humidity, and then we have a jump, suddenly, water uptake, right? It's very sudden, like you flip a switch. And then, so see how this ratio now has increased to about 1.4. And as you add more water, relative humidity, as you increase the relative humidity higher, this diameter ratio increases quite steeply. So the particles are dry until you hit 80%. That's the deliquescence relative humidity for ammonium sulfate. And then they grab water very rapidly or efficiently and grow quite a lot. And so you probably have seen the evidence of this when you have a humid day and you see like hazy conditions, right? So that's aerosol particles that have taken up a lot of water and they scatter radiation very efficiently. And so you see this visually as a haze, versus when the particles are dry, they are really small, right? And so they don't scatter radiation that efficiently, so you don't see it as this hazy conditions. So now, next time you see hazy conditions, you remember that, okay? This is not the end of the story. It gets even more exciting. Can you imagine this? If we now start up there and decrease the relative humidity. So you would maybe think, okay, let's decrease the relative humidity. We go back, and now we dry, right? Whoops. When we hit the 80%, we jump back and all the water gets expelled and they become dry again. This is not what happens. So instead, we keep going along here until we hit something like 35%, and then we go back. And so that phenomenon is called hysteresis. It's a hysteresis phenomenon. Then the going forwards and going backwards is not the same, right? So you're not going on the same path. So we have a little hysteresis effect here. So this would be called the deliquescence relative humidity. And that's the efflorescence relative humidity. And they are not the same. Okay, so this was ammonium sulfate. In contrast, here's our sulfuric acid that we talked about before. It really likes to take up water. That doesn't have these step function behavior, right? It starts out at low relative humidities. Even at low relative humidities, it can grab a little bit of water. So this ratio is never 1 here, right? It already starts at 1.2, and then it sort of like increases smoothly. It doesn't have this behavior that the other salt has. So that's a little bit of a different type. But many other salts or electrolytes have that behavior, and the deliquescence relative humidity is not the same, right? It varies depending on what the relative humidity is. And so if you build such a thermodynamic model, you have to take account for all of this, right, in one way or another. So with the chemical potentials. Okay, so that's just showing you again, if something is solid or liquid, again, there is the Gibbs free energy is the key here. For an aqueous solution, as you go from low relative humidity to higher, it decreases. For a solid, it's constant. And so at some point, there is this switch over, right? So, and that's why you change from being a solid to being a liquid, because then your Gibbs free energy becomes lower. All right, so we talked about this already, so we can, this is just with more words annotated, what I just said, so we can go through this. 10 slides right here. Yeah, and so for sulfuric acid and ammonia water system, the key point that I didn't mention here is so to actually form ammonium sulfate, you need twice as many moles of ammonia compared to sulfate, right? To fully neutralize it. And only then can you have ammonia left over in the gas phase. If you have more than this ratio of R is the ratio of sulfuric acid to ammonia. So as you go through these different regimes, you can take up all your ammonia, draw it into the aerosol phase, and only if you have more ammonia left than twice the amount of sulfate, right? Makes sense. You can have the ammonia in the gas phase, otherwise it all gets taken up by the sulfuric acid, forming ammonium sulfate. Okay, so the other system now as fundamental, right, is then ammonia, nitric acid, and water. It's also 3 things, but rather than sulfuric acid, we have nitric acid. Similar idea, but it's different because the ammonium nitrate is formation is very temperature dependent. So if the temperature is low, ammonium nitrate likes to be in the aerosol phase. If it's higher, ammonium nitrate goes back into the gas phase. And that's not the case for ammonium sulfate. It's not very temperature dependent at all. So ammonium nitrate is very volatile and goes back and forwards. Between gas and aerosol. So for example, in the morning when the air is cooling down, you may have enough of the precursors and the temperature is cool enough that you can form ammonium nitrate, but then when the air is warming up, it evaporates and you have the nitric acid and the ammonia back into the gas phase. Similarly, if you think about the vertical structure of the atmosphere, it gets cooler as we go up, right? So it might be that in the surface level, you don't have any particulate ammonium nitrate, but everything is in the gas phase. And as you go up, you are able to form ammonium nitrate, and it condenses on the existing particles right there. Ammonium nitrate is also an important pollutant during the winter time for that reason. And for all of us in the Midwest, we had bad air quality episodes because of ammonium nitrate formation during winter time when it gets cold, and the ammonium nitrate can be in the particle phase rather than in the gas phase. Okay, let's not worry about this example. All right, so this was a little, very quick overview how we handle the formation of ammonium sulfate, ammonium nitrate, like the inorganic secondary aerosol in these air quality or global larger scale models where we assume a thermodynamic equilibrium, right? So these are the kind of tasks that we have to sort of like replicate that system. Now, in the last 20 minutes maybe, let's move on briefly at least to this big area of organic aerosols. And let's come back to some basics because it's also close to what you are doing with your combustion and soot formation. So these words float around a lot. So black carbon, elemental carbon, organic carbon. So let's try this out and with your neighbor, talk to your neighbor and try to explain to them what the difference is, right, between black carbon, elemental carbon, and organic carbon, and how these words are used. So let's just brainstorm a little bit for just a couple of minutes.
Elemental carbon is carbon that's found in that ground naturally. That's not.
You can't find. I mean, you can find elements of like.
Yeah.
I don't think you'll ever find like you won't ever find just like a carbon. You'll find probably like
No, you won't find it. But I think, yeah, elemental carbon is just carbon. Individual carbon. Black carbon is carbon that was probably.
This kind of. I was thinking, I'm not sure, but I was thinking about.
Wait, it's a combustion process, or like the.
Like you can have like
yeah, I mean organic carbon
aromaticity. Like you can have like carbon structures, but they can be arranged in different ways. Usually, for example, the most pure one. It's like a like a really well-defined aromatic structure. Maybe I was thinking about that. Maybe you have like, for example, charcoal. When you have it, it's like quite aliphatic. So just like carbon.
Wait, you're asking organic carbon what
The more you heat it up.
That was a joke.
Because it really affects the stability. Like the aromatic structures are like way more stable, and the aliphatic ones are easier to break. Maybe that's quite important. I don't know, but it's just a guess.
You gotta say it.
What's your opinion? I think we should put some black carbon. I'll get a match.
Yeah. All right, this is right up your alley. You know a lot about all of these. So let's see here. Let's start with organic carbon. So organic carbon is, as the name says, carbon content in organic compounds that is found in aerosol particles. So there's a lot of alcohols and acids and hydrocarbons and oxygenated organic. So there's O's and like oxygen and hydrogens attached to the carbon in one way or another, right? And again, we have primary sources of this. So fossil fuel combustion would be considered a primary source of organic carbon. there's also biogenic sources. And secondary means it's formed in the atmosphere from other gas phase precursors, volatile organic carbon precursors. And in terms of properties, goes in and out of aerosol phase, back and forth aerosol and gas phase, can take up some water, although it's not as hygroscopic as some of these inorganics that we just talked about. Usually it's not light absorbing or only maybe weakly light absorbing. There's also this thing called brown carbon these days that people research, which we don't need to worry about for now, but that is a more light absorbing variant of organic carbon. Okay, so that's that. Now, black carbon. So that's also, again, is your byproduct from the incomplete combustion, right? So that is the portion that strongly absorbs the visible light, which is called black, which is why it's called black, right? Because it's black. And it's somewhat operationally defined, right? So it's defined by its ability to absorb light. So when you have your aerosol sample and you measure optically how much radiation is absorbed by your sample, that's how you figure out how much black carbon you have, right? And it's another thing is, in terms of properties, it doesn't like to absorb. It's not very hygroscopic, or it is hydrophobic when it's freshly emitted. But as it's exposed to the processes in the atmosphere, it can actually change, right, and become more water liking, so more hydrophilic, and for example, become CCN. So now the tricky thing is, what is elemental carbon then, right? If this is black carbon. So that is also has to do or is defined operationally, but rather than based on light absorption, it has to do with how easily it volatilizes after being exposed to high temperatures. So you exposing your sample to high temperatures, the organic carbon evaporates. Whatever can evaporate evaporates. What's left behind is called the elemental carbon. And as a student, I was often very confused about this. Like, is this the same? Is it not the same? So it's not the same, right? It's so elemental carbon and black carbon gets often used interchangeably, but it's actually not the same, depending on the conditions. So if you measure the black carbon in a sample with your light absorbing methods, you get a certain result. If you use the same sample and measure the elemental carbon based on the thermal methods, you may not get the same microgram per cubic meter, right? So that's one of the struggles, and there are actually many papers that try to relate one to the other and really examine what are the differences depending on how I measure it, and that is very instructive. And I really like this figure from one of these papers. It's now a few years old, 20 years old, that sort of like puts this into context, right? Starting out with the molecular structure, which you know a lot about. And on the one hand side, you may have the thermochemical classification going from non-refractory organic carbon to elemental carbon, and then the optical classification going again from organic carbon that doesn't absorb to black carbon that strongly absorbs, right? And you can relate this to the molecular structure. I heard for black carbon and elemental carbon, you have these graphene layers, right? And you are in the middle here, you have the polycyclic aromatics and so on and so forth. And it's a continuum, right? It's a continuum here and there. So this is how these are related. Okay, another exercise for you. Now looking at maps of different aerosol components. So there's no black carbon in here, but there is soil, which is sort of like, soil, soil type aerosol, organic aerosol, ammonium nitrate, and ammonium sulfate. So 4 different main components of the aerosol, and which one is which? Which spatial distribution corresponds to which one? So think about how they are formed, and you can talk to your neighbor as always. I want to hear conversations.
And here on the west, because there's nobody there, it's pretty empty.
No, I disagree with you. What do you think it is? Well, one, California has like the highest population of all.
Yeah, but they also do a lot of electric stuff.
I mean, it's also, this is incorporating mainly Appalachia, which has 0 production, 0 people. I think that this might be organic aerosol from farming.
I said this was black.
It's black.
So which one do you think is soil? Soil is probably easiest, maybe. So which one? This one? Soil? Who thinks this one is soil as well? No? Disagreement? I hear disagreement. Other offers? Where's your soil? Yeah? This is soil? You've got another person who agrees? I saw shaking heads somewhere though. What do you think? The bottom left? Why do you think the bottom left?
Sandstorms.
What was it?
Sandstorms.
Sandstorms. It doesn't have to be necessarily storms, but the dry, your reasoning is the dry areas of the US, right? The dry southwest, and that's true. So that's your soil right here. Okay, what about the other ones? Does anyone want to take a stab for one of the other ones? Think about where, yeah? Top left, ammonium nitrate. Other offers, yeah?
I was wondering if the top right might be ammonium nitrate, because most of the regions that are high enough there are farming regions.
Yeah, so this is, you have to know Midwest, is a big farming. Bullhole, yeah, ammonium nitrate. Okay, two down, 2 to go. What do you think about the organics and sulfate? That's a bit more tricky, and they look quite similar, the remaining ones, right? But any thinking?
Left is ammonium sulfate because of the industrialization of that area.
Yeah,
That's the Appalachian.
good reasoning right here. And then the last one is the organic content. Yeah, the organic aerosol. And let's see if I did it right. So here's the solution. Okay, ammonium sulfate, we got that. Nitrate, yes. Soil, and then the organic fine mass. So what's happening in the south here?
Agriculture and flooding, agriculture, plowing up the stuff.
There's other things too in the southwest.
Oil fields?
What was that?
Oil fields?
Think more about forests. There's lots of forests actually, and those forests, they are emitting volatile organic compounds. We haven't talked about those much, but there's actually a lot of gases come from vegetation, right? They are emitting a lot of organic, so-called VOCs, volatile organic compounds, and those react in the atmosphere and then form something that is less volatile and then condenses as secondary organic aerosol. Yeah, so it's quite interesting to look at this this spatial distribution of just the main. We don't need to even talk about individual particles, but just the main distribution of the main components. Okay. How much time do we have left? Yeah, there's a zonal distribution here, just to hammer home the point about black carbon. Yeah, so speaking of the forest fires keep coming up, of course, there are really major events happening and really interesting scientifically, of course. They are emitting both black carbon and organic carbon. And when you see a plume like this, what do you think that is made of? Is it black carbon? Or if it looks white like this, right, this is organic carbon. So depending on, and then there are other fires like this, right, that emit a lot of black stuff. So this is your black carbon now. And interesting thing is it has to do with the way the fire is operating, right? If you have flaming conditions, you're producing larger black carbon cores and thinner. It's always a mixture of black carbon and organic carbon, right? But the ratio is different, and therefore it looks different and also has different properties. So for a smoldering fire, that will produce less black carbon and thicker coatings of organic carbon. And there's lots of fires all around, right? So there are satellite remote sensing products that tell us where they are, and so that's just an example here. And if we look now, I can't resist, of course, showing you these particles, which you probably have seen before coming from your background. But depending on how we produce or what phase the fire is in, so they were burning maize straw in this case, right? In the smoldering phase, the particles look like this if you look at it with a microscope, and in the flaming phase, they look like that. And so you can actually analyze, what the different, if you take one particle, it has these different bits to it, what they are made of. So there's organic matter, soot, but also other components containing chloride and sulfate, and lots of sophisticated analysis tools that people use, right, to really get into the details what these particles are made of. Yeah, so organic aerosol composition is very overwhelming. So I'm just showing you now pages, and we don't have, this is just to hammer home the point that there's so many different components in what we call primary organic aerosol. Look at this. So this is one table, and it's from a long time ago, right? So even at that time, they analyzed this, pages and pages, table is still going on. Here's the rest of it, and they have grouped it in different types, right? So there are acids and PAHs and other things. So yeah, so the chemists are doing a really good job. So this is what we talked about before. Where do these aerosols come from, right? I mentioned the tire wear, right? There's another group, actually, and I found this surprising as a student when I first heard about this, meat cooking. I didn't mention that. So meat cooking produces these kind of things like cholesterol and certain organic acids, right? And so it's organic material that gets emitted from establishments that cook meat, or when you have a barbecue next time, think about all the meat cooking aerosol that you are releasing into the air. So that's another actually really important source. I forgot when you asked, I forgot to mention that. Yeah, instrumentation. I'm not the right person to explain this to you, but I really like this slide that was made by a colleague, Jose Jimenez, trying to bring home the point that there's a trade-off, right? A trade-off between how many types of species an instrument can identify, and how complete the organic mass can be analyzed, right? Ideally, in a perfect world, we want to identify all the components and all the organic material, right? So we would be in this upper right corner. But no instrument actually is in that corner, right? So you have to make trade-offs. If you really want to identify things on a molecular level, which some of these instruments can do. So GCMS is gas chromatography, mass spectrometry. They really get like a lot of detail, what is in your organic aerosol, what are the different components, but they can only identify a small fraction of all the organics, right? Then there are other instruments. On the first day, we had this exercise about the mass distribution that came from an AMS. So that's up there, AMS. It analyzes the organic mass fraction almost completely, right? But you only get a few classes. It's not as exhaustive as some of these other methods. So it is really a challenge, and it's a lot of research going into this field. So the secondary organic aerosol is also one big area in our field. So some of the questions that people ask, what are the precursor gases, right? So are they being emitted from anthropogenic activities, or do they come from plants? So the anthropogenic and biogenic division is very interesting. What are the mechanisms, right? So how do these gases have to react to form something that can condense into the aerosol phase? How do we simulate this, right? How do we put this in a model? What are the properties? Are they good at forming clouds? Do we have to worry about it when we do our global model simulations and want to know how many cloud droplets we form? Are they active in ice formation? Do they absorb light? To what extent? What's their refractive index, right? So real and imaginary part. Okay. This is just an overview showing you from the secondary organic aerosol. It can have biogenic sources, so precursors here, anthropogenic sources. You have the interaction between both. You form different SOA components. They can have actually very different properties in terms of how volatile they are. Are they solid or liquid? In what kind of phase are they? They play a role in your particle formation that we talked about, in the growth of aerosols. We haven't talked much about heterogeneous and multiphase the chemistry, actually. That's for another day. And then going into the impacts, right? So their lifetime in the atmosphere, how do they impact clouds? How do they impact the radiative balance? And then eventually, these are the climate impacts. And as the climate is changing, so that's an interesting thing maybe for you to think about, right? As the climate is changing, we are changing the sources, right? Also, so it's a complicated system. And our tools, right? Lab, modeling, and field studies, always working together. And so what happens in our models, so there's so many different species, so we can't treat them explicitly, right? So often we would lump them. So that's what that means, surrogate species. So we lump them together. To form a manageable number of surrogate species. And another big question is like the reaction pathways, right? So just the precursors, and then also when the material is in the aerosol phase, they keep reacting. And so there's so many open questions, and it's a really active area of research, lots of papers being published just on this one topic on secondary organic aerosol. Okay, so 10 minutes or so left. So we talked a lot about our different processes and how we we wrangle them to put them into our equation. And the last step now is the numerical model, right? So, and we already know about the different types of models. Let me see here. I just, maybe for the last few minutes, I want to spend on, given that these modal models are so prevalent in many of the global models, they are very efficient. I want to spend some time explaining to you how it works. But this is really fast. So the task is, we say the total aerosol distribution with our different modes can be represented by several log normal functions. And so there's a lot of choice here, how many log normal function one uses. It's typically motivated by the aerosol types that you want to represent, right? So you might have a mode for your, this black one is your freshly emitted dust, soot from the combustion engine. And then you have maybe 2 modes for particles that do not contain any soot and are just there from the background, right? And then you have another mode that is your sea salt, maybe, and another mode that is your dust, right? So maybe for a certain application, this would be the right choice. And you already see there's a lot of subjectivity here, and different people might choose different sort of basis function, right? So to represent your overall population. But the goal then is to predict how these functions evolve in time, right? Because that determines what this overall size distribution looks like. And if you think about a log normal distribution, what it comes down to is there are 3 free parameters that we need to figure out, right? It's the total number concentration, that's the capital N. It's the width of the distribution, that's the sigma. And it's the position, it's the geometric mean diameter that determines what this mode looks like. And so then what one does, so that's a slightly roundabout way. So maybe the more, what you then, maybe knowing this, you would say, okay, let's formulate an equation for N, for sigma, and for dp, G, right? But especially for sigma and dpg, that's not so easy. And rather what we do is we use this fact that if you know 3 moments of your distribution, you can always figure out what these 3 things are, right? Do you know what a moment is of a distribution? So a moment, you have the distribution here and you multiply it. So it's a function of dp in this case. You multiply it by dp to the power of k. So that would be the kth moment of the distribution, right? So the 0th moment is actually the total number concentration. The second moment is proportional to the surface concentration. And the third moment is proportional to the total volume concentration, right? So the way these modal models work, you formulate prognostic equations for these moments. And from that, you sort of like reconstruct your sigma and your dp. The n is already the 0th moment, right? So you calculate that directly. So that's how they work. And the power of this method is you can actually, with appropriate little simplifications, do a lot analytically, because the log normal distribution is nice. You can calculate, these integrals appear a lot, right? And so these you can analytically integrate this integral if this is assuming that n is a log normal, right? And believe it or not, it actually is this result. You get this result. So that's the principle of modal models. Yeah, so you take our governing equation that we looked at many times, multiply it by d to the power of k, so that you create basically the moment, and then you integrate over the diameter. And then you get a whole bunch of equations that you solve for the first moment, for the second moment, and the third moment. And so, yeah, that's how these models work. And there are a few wrinkles to it. What do you do with coagulation, where you put things from one mode into the next mode? So that's where it becomes a little bit tricky, but people deal with it. And yeah, so different model approaches. This is the EPA model, has 3 modes, right? Different species can live in different modes, and so different processes happen in different ways. Another model that is used in the global, one of the global models from Europe, they use 9 modes, right? So it becomes more complicated, but they can treat different types of particles. So I already mentioned this. Sectional models, very similar. You formulate basically a budget equation for each section. And lastly, our particle resolved models, where we don't have any modes or bins, so we set the particles free, right? And so that gives us much more flexibility. And a lot of processes that we want to then replicate or represent become stochastic sampling exercises, right? For example, coagulation becomes a sampling exercise. So we treat our coagulation coefficient as a probability of coagulating. And then we basically test pairs of particles and see, do they coagulate or not? And if we have a lot of particles in our system, computational particles, we have to have methods so that we don't have to actually check every pair, because otherwise you'd spend a lot of time on checking pairs. So we had to develop accelerated methods to do this efficiently. Okay. Yeah, I wanted to show you this maybe at the end here. Yeah, so before we talk about the limits are basically, they are computationally expensive. I wanted to show you, coming back to this idea of composition space, right? Because I told you this is, if there's one thing that you remember from this course, it's this, okay? So up here is our size distribution again. And so there's a number size distribution and a mass size distribution that you are very familiar with now as a function of diameter. But this is a projection, right? And so what we do, another way we can display our results here is, so we were interested in black carbon for the many reasons we talked about. And so the way we display our results from our particle resolved model is like this. So we project it into 2 dimensions. So this is still a projection, but it shows you how the black carbon mass fraction in the particles changes with diameter, right? So a 2-dimensional projection of the higher dimensional particle population. So size still on the x-axis. On the y-axis is black carbon mass fraction. And then the color is how many particles you have in each of these two-dimensional bins. And so you see, I don't know if you can see this from the back, but there is like a line here where black carbon mass fraction is very low. And there's red colors right here. So there are a lot of particles that actually don't have any black carbon in this simulation. And then if you go to a certain size, so 0.1 micrometer, 100 nanometer, there's a whole continuum, a little maximum here. So lots of particles have, let's say, 10% black carbon. And there's many particles that have all kinds of different mass fractions, right? Going from 20 to up to 70. And nothing had 100. So this has to do with how we initialize our particles. And so you can project the same thing onto this axis, and then you get this figure, right? So most particles have actually 0, no black carbon, and then the black carbon containing particles have this concentration distribution right here. Yeah, and so in the modal models and sectional models, you are collapsing this axis down, right? So you don't see how they are distributed in that dimension. Yeah, and so the limitation that we have to face is how do we make this method go fast? And so we developed a whole bunch of computational methods to do this, and also methods to run the code in parallel on many processors to accelerate this, but no question, it is computationally expensive. Okay, I think we did it. So we went from the real world phenomenon. I got you acquainted with many of the processes, how to formulate the governing equations, and then how to actually implement this into models, and some of the challenges and fun things about that. So I think we are done. Thank you for your attention, and I hope you have a good rest of your summer school now this afternoon, and safe travels home. Yeah, thank you.